Hello everyone, and welcome back to another tutorial quiz. So in this tutorial, we're going to be covering quiz number 7, which deals with orthogonal tensors. And the first question I know a lot of you have is, what is a tensor? Well, basically, a tensor is a matrix. So if you ever see tensor, just think of a matrix. Tensor is just a fancy word to kind of make you feel a little bit smarter. But usually if we have a 3x3 matrix, we just call it a tensor in continuum mechanics. So orthogonal tensors are very important in continuum mechanics because, as you guys will see, the coordinate transformation matrices, those Q matrices that we use to change basis, well, they're often orthogonal tensors. And as such, we can do a lot of very nice, easy calculations and simplifications with them because they have a very unique set of properties. So to show you guys these properties, let's jump into the theory. All right, so if Q is an orthogonal matrix, it has a very specific set of properties. The first one is that the transpose of Q multiplied by Q is equal to the identity matrix. And this is very important because this is the definition of an orthogonal matrix. So if you ever asked to prove, is this matrix orthogonal or not, well, we're going to use this property right here to prove that it is. The second one, which I want you guys all to remember because this one will be very important for midterms, is the determinant of Q is equal to plus or minus 1. And whether it's positive 1 or negative 1, well, that also means something very specific that we're going to cover in the next slide. The next two are fairly similar, and as the rows and the columns of the matrix are orthonormal. So each of the vectors that make up the rows and columns of the matrix, well, they're perpendicular to each other. And you guys will see an example of this on the quiz. And finally, the product of two orthogonal matrices is also orthogonal. So these are kind of the 5 big properties of them. But the two that I really want you guys to remember are the first two. Again, the first proof that the transpose of Q multiplied by Q is equal to the identity matrix. That's the definition. So if you're ever able or ever asked to prove that the matrix is orthogonal, that's what you're going to go to. And then the second property, that determinant of Q, will also be very important for the quiz, but also for the midterm. And you guys are going to ask yourself, well, why is that one so important? Well, if we look into it, there's two possible scenarios. The determinant can equal to positive 1 or negative 1. And this is why it's so important. If the determinant is equal to positive 1, Q is associated with rotation. So usually in a midterm, or as you guys will see in the quiz, it's going to be the opposite way around, where the question will state that Q is a rotation matrix. And if it states that, then you guys can say, okay, it's a rotation matrix. Therefore, the determinant of that matrix must be 1. And again, this is if the matrix is orthogonal as well. Not just any rotation matrix, it has to be orthogonal as well. And then the opposite can be said if it's equal to negative 1. So if the determinant of M is equal to negative 1, Q is associated with reflection. So again, a very typical midterm question would be Q is associated with reflection. What is the determinant of Q? So a lot of people will actually look at the matrix, and who knows, maybe Dr. Samuel will give you a matrix and you guys will be doing all the calculations. When, for instance, it's actually really trivial, you guys can just jump to the conclusion that the determinant of M is equal to negative 1. So to help show you guys these in more of a question format, similar to what you guys would see on the midterm, let's jump into the quiz. Alrighty, so we got a nice easy quiz, 5 questions, and all the questions are very simple in the fact that they don't really test your numerical abilities, they test your knowledge on the properties of orthogonal matrices, which is perfect because I guarantee you guys are going to get a lot of midterm questions on this topic. It's a very important topic. And the midterm questions will actually be very similar to the quiz here. So if you guys understand the quiz well, then the midterm is going to be no problem for you guys. So if we look at question 1, it says if Q1 and Q2 are reflection matrices and Q3 is a rotation matrix, which of the following is false? So the first thing that we're going to have to recall is that determinant thing that we discussed before. So if Q1 and Q2 are reflection matrices, well, then we know that the determinant, so the determinant of Q1 is going to be equal to the determinant of Q2, because remember, all these are the same if they're orthogonal, and this is going to be equal to negative 1. Because again, that's if they are a reflection matrix. Now, it says that Q3 is a rotation matrix. So from this, we could conclude that the determinant of Q3 is equal to positive 1, right there. So these are going to be kind of the properties we need to solve this question. So the first part of the first answer is the determinant of Q1, Q2, and Q3. Oh, and I forgot to put it. It says in the question that this is equal to 1. So we're going to verify that that's equal to 1 or if it's not equal to 1. So if you guys remember, the determinant of 3 matrices put together like this, Q1, Q2, and Q3, in this case, is just going to be equal to the determinant of all three of those matrices multiplied by each other. So in this case, we're going to have -1 times -1 multiplied by 1. So -1 times -1, well, that turns positive, multiplied by 1. So this is equal to 1. So if we go up here, the question A states that the determinant of Q1, Q2, Q3 is equal to 1. Well, that's exactly what it is. So in this case, this is absolutely correct. Now, part B, Q, which is equal to Q1, Q2, and Q3 is invertible. And this is true because remember the fifth property that I discussed, which is kind of the property most people forget about, is that the product of two orthogonal tensors is also going to be orthogonal. And if it's orthogonal, then it's, of course, invertible. So if we multiply three tensors together, three matrices together, well, it's also going to be orthogonal, and therefore it's also going to be invertible. So in this one, this is also true. And if this was a midterm scenario, you guys can kind of guess it's either going to be one of C or D, because one of them says rotation and the other one says reflection. So there's kind of a very, I guess, line in the sand there where it's going to be one or the other. And this is where we have to go back to the determinant. So if you guys recall from question A, or I guess part A, we found out that the determinant of that is all going to be equal to 1. And if you guys remember, if the determinant's equal to 1, it means that that resulting matrix is associated with a rotation. So in this case, part C, where it says that the Q is equal to a rotation matrix, this is true. And this is because that determinant is equal to 1. If we go to part D, where it says Q is a reflection matrix, we know that this one is absolutely wrong because the determinant is equal to 1. So it's associated with rotation. If the determinant was equal to -1, then statement D would be correct. But since it's not, we can conclude that the false one here is going to be D right there. All right, so let's move on to question 2. And I put it as question 2. It's actually question 3 in your quiz. I just wrote this down and kind of forgot, but this is actually question 3 for you guys, but we're going to say it's question 2 for me. And it says, let Q and M be three-dimensional matrices, and let N equal QM times Q transpose. And if you guys look at this right here, this should be very familiar to you guys. And we'll talk about that in a second, but just look at that and that should kind of ring a bell to you guys. And assume Q to be a coordinate transformation matrix, which is orthogonal, and which of the following is true. So if we look at that statement right there, if N is equal to Q times M times Q transpose, where Q is a transformation matrix, you guys should kind of have little bells going off and say, okay, this is associated with a change of basis. Change of basis. Because remember, if we had a matrix in one basis and we wanted to transform it to the next matrix, we use this formula exactly. And it's reinforced with the fact that Q is a transformation matrix. They kind of give that away right here. And from here, we can conclude another thing. If we have a change of basis, remember that there's going to be three things that stay the same between those two matrices N and M, and those are the three invariants. So even though this is quiz 10, it kind of goes back to quiz number 9. So if we come up here and we say, okay, N and M share the same three invariants. And if we look at these, well, they kind of look like invariant type questions. So it wants us to answer which of the following statements is true. So if we look at part A, or statement A, it says the eigenvalues of M and N are the same. And if you guys remember from quiz number 9, this is true. Eigenvalues are an invariant. They do not change even when the matrix changed basis. So this statement right here, absolutely true. The second one is the diagonal components of M, the summation of the diagonal components of M, are equal to the summation of the diagonal components of N. So in other words, this is saying that the trace of M is equal to the trace of N. And we know that the trace of a matrix is actually that first invariant. And since invariants don't change, we can conclude that yes, the second statement is also true. Going to statement C, the determinant of M is equal to the determinant of N. Well, if you guys remember, the third invariant is exactly that. This is basically saying that invariant 3 of M is equal to invariant 3 of N. And as we know, the invariants don't change. Therefore, this statement is definitely correct as well. And if we look at statement D, it says all of the above are correct. that's exactly what we got. We can conclude that yes, all of the above is the correct answer. All right, moving on to question 3. So for you guys, this would have been question 2. Again, I just wrote question 3 down first by mistake, and I didn't want to have to erase and rewrite it. So question 3, again, question 2 for you guys, says let Q equal a 3-dimensional orthogonal matrix with components D1, D2, D3, E1, E2, E3, and F1, F2, F3. And I just want to kind of highlight to you guys really quick that these are not basis vectors. These are just a placeholder for the name. They're not the basis vectors E1, E2, and E3. And it says if D is equal to the first row, so again, it's saying that D right here, oops, that's not what I wanted. I wanted the highlighter. So if D is the first row of the matrix, E is the second row of the matrix, and then finally F is the third row of the matrix, which of the following statements is true regarding these 3 vectors? So this comes to properties 3 and 4. So remember, if this is an orthogonal matrix, which it is, the rows are orthonormal. So rows are orthonormal. Sorry, guys, it takes forever for me to write. Orthonormal. So if they're orthonormal, I'm making no sense. If they're orthonormal, that means that each of the vectors in those rows are perpendicular to each other. And if they're perpendicular to each other, that means that the cross product between them is 0. So D dot E is going to be equal to E dot F, which is equal to, I guess, D dot F. And all this are equal to 0 because remember that property states that if we have an orthonormal matrix, then the rows are orthogonal to each other. So if we come down to here and we see our possible choices, we can say that, okay, statement A says that D dot E, blah, 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 is equal to plus or minus 1. And we know that that's not true already because we just talked about above that since these rows are, the row vectors are orthogonal to each other, the dot product should be 0. So this should be equal to 0, not plus or minus 1. So we know that statement A right here is actually false. So statement A, it's false. The second one, well, actually, let's go to statement D really quick. Statement D is really nice because it says both A and B are correct. And since we already know that A is false, we can say that D is also incorrect. Because remember, we're trying to find the true statement. And if we come down to B and C, well, it's going to be obvious it's going to be one of those two because it kind of gives you an ultimatum. It says that E dot F cross D is equal to plus or minus 1, and C is the exact same except it's equal to 0. So for this one, it's actually really easy to see because remember that a cross product gives you an orthogonal vector. So in this case, if we were to go F cross D, it's going to give you an orthogonal vector, which we know is equal to E, because we already know that E is orthogonal to those 2 vectors. So what the statement's really saying is, what does E dot E equal? Well, since they're also orthonormal, they're normalized, this is equal to the magnitude of E squared, and this should be equal to 1. So if this is the case right here, we know that B is going to be our correct answer. This one right here, that part C, that's not correct. So that's question 3. Again, question 2 for you guys. Hopefully it's not too bad thus far. I hope I'm not scaring you guys away. But again, these are just has to do with properties of orthonormal basis. And if you guys look at the sample midterm questions, they're littered with these orthogonal matrices questions, especially the ones like part A where you got determinants of a bunch of different things. It's easier than it looks. Looks really scary, easier than it looks. So what we're going to do is we're going to come down to question 4. And question 4 is a lot of fun because it's actually a really simple question, but it can be used to scare a lot of students. And it says the figure below sketches the process of rotation of any vector by 30 degrees in the counterclockwise direction. What is the rotation matrix Q that can apply such a rotation? So it makes it sound really scary. We're going to have to find all the components of Q, but it's actually a question we've seen before. So if we look at the first figure on the left, this is our regular E1, E2 basis, and we have vector U. If we look at our our diagram on the right, all we see is that we took U, rotated it 30 degrees to give us that new purple vector QU. So here's kind of the trick to these questions, and you guys should remember this because this will basically appear on your assignment. So be ready for this. Let's look at this figure right here, and I'm going to zoom in a little bit right here. So what I did is I just took the second figure where I took u and I rotated it 30 degrees. And we have to realize that this is actually the same as if I took the basis right here. Actually, what should I do for the new basis? Let's go pink. And what I should do, I'll go pink. And I'm going to switch this to dotted. All right, here we go. This is a new feature, apparently. I was told about this. So rotating a vector counterclockwise is going to be the exact same as rotating the basis clockwise. So what do I mean by that? Well, as we can see, by rotating that vector u, that new vector qu became closer to e2. And I don't know why I got e1 here. This should definitely be e2. And it went to the squiggle line. All right, let's try and fix this. All right, so after we rotated that vector, it became closer to e2. Well, that's the exact same as if I rotate the basis the opposite direction. So let me rotate the basis. Actually, we'll go like this. And then this will come down. So if I were to do that and rotate the basis where, I'm going to switch this. Squiggles sound like a good idea, but they take too long to switch back and forth from. So if I were to rotate the basis e2 this way, well, we have the same result where that u vector became closer to e2. So it's really hard to describe. What I recommend is you guys draw a picture of it yourself. So what I'm going to do is I'm just going to kind of give you the statement right here. So rotating, oh, this is going to take me forever to write. I'm sorry, guys. Rotating a vector clockwise, and the vice versa of this statement will also be true, clockwise, that's the equivalent of rotating the basis counterclockwise. Again, it's kind of hard to see because I myself had to draw a picture and figure it out a little bit, but kind of the main way I showed you guys is if we were to just take the, if we were to just do this transformation, look at QU, it becomes closer to E2. Now, instead of doing that, what I can do is I can say, okay, if I want E2 closer to the vector U, I can just rotate E2 that way. So the vector would have been rotated this way. However, the basis is rotated the opposite way. And you guys will actually see that on your assignment. So you guys are going to kind of have to know it. So if we're rotating a vector clockwise, well then the matrix that would transform it, or the rotation matrix, will actually be the same as the rotation matrix for a counterclockwise rotation. So I'm not going to show you guys the derivation of this because it's in the other videos. You guys can find it very easily. But what you guys will see is that Q is going to be equal to the cosine of 30 on the top. On the bottom, we're going to have the sine of 30. And then on the other side, we're going to have negative sine of 30. And then on the bottom, we're going to have cosine of 30. So again, this matrix, how did I figure this out? Well, I realized that if we're rotating a vector clockwise, it's the same as rotating the basis counterclockwise. So because of that, I just took my counterclockwise rotation matrix that I've already figured out in, what was it, I think quiz number 7, and I just copy and paste. So it should be an easy question. Now, question 5, this is the question that'll get a lot of students because you guys are so used to rotating the basis by an angle theta. So if they gave you theta is equal to 30 degrees clockwise or 30 degrees counterclockwise, I know you guys are all laughing. Oh, I have my matrices, I'm good to go. But now we have to consider an orthonormal change of basis from B to B prime, where instead of giving us an angle theta, they gave us the new components of B prime. So if we look here, we have our original basis, which is E2 is equal to 0, 1, and we have E1 is equal to 1, 0. So this is always such a typical choice of an original basis. And usually they give us those two and they say, okay, what happens if we rotate by angle theta? But this one's a little bit different. In this question, they don't give us an angle theta, and they say, well, the new basis, E1, is equal to 0.8, comma, negative 0.6. And E2 prime is equal to 0.6 and 0.8. And it wants us to do the same thing as before, or what are the components of U prime in this new basis set? So you guys already know that to find u prime, it's just going to be equal to q times u. And we already have u, so the question becomes, all right, what is q? Because usually, I know you guys just copy the rotation matrices and go from there, but this time we don't have theta, we don't know what to do. I guess if you're feeling really ballsy, you can try and just find theta using the trigonometry, that would work. But if you guys want the kind of the proper proof of this, we're going to have to go to the definition of theta. So recall, sorry, the definition of q, definition of theta. Oh, I am losing it. All right, so we remember that q is equal to e1 prime dot e1, and then e1 prime dot e2, and then on the bottom we have e2 prime dot e1, and then e2 prime dot e2. So this is just simply taking the dot product between a bunch of vectors. And I already know you guys know how to do that very well, so that's all you guys are going to have to do. But here's kind of the little trick. If e1 and e2 are equal to those standard, I just call them the standard basis vectors, 1, 0 and 0, 1, then what happens is the first two entries are just going to be the first components of e1. So the first components of e1 are just the entries of e1 prime. So we have 0.8 and we have negative 0.6. And that's because the e1 and e2 are 0, 1 and 1, 0. And similarly, the second components, or the second row components of q, are just going to be the components of e2 prime. So e2 prime is 0.6 and 0.8. So I can come down here and I just go 0.6 and 0.8. So now I have my q matrix. So I'm just going to finish that up nicely. And then all I have to do is multiply that q matrix by u. And what you guys will find is that u is going to be equal to, and I'm just going to come down here and draw my sign like this. I am not a fan of drawing the brackets, but what you guys will find is this is equal to 0.2 and 1.4. So I just did this in my calculator. Of course, you guys are smarter than me. You guys can easily do it in your head or by hand, but I don't know. I'm always a suck for just throwing it into my calculator. So this is what I got. Again, this question is great because instead of theta, it actually gives you the new basis vectors, and you guys are going to have to kind of remember this definition, and I'll kind of circle it right here. Remember this definition right here. This will be very important in case you guys are not given theta. But again, if you guys are feeling really ballsy, then you guys can just use trigonometry to calculate what that rotation was. So that's it. That concludes quiz number 10. I hope you guys learned a little something about orthogonal matrices. And if I were to give you guys kind of a last minute hint, look at question 1. I've seen this every midterm I can imagine, where they give you a bunch of different matrices. They say if they're reflections or rotations, and then they ask you the determinant of all those matrices put together. So this is such a classic question. It scares a lot of people because once they start seeing a lot of matrices, they think, oh, this is going to be very calculation heavy, when it's actually not. It's very, very simple. So thank you guys so much for listening and making it to the end of this video. I will see you guys in quiz number 11.